Hi, everyone, and welcome to Tablet Time. Let's go ahead and do a couple of the problems together here so you can kind of make sure you understand how to go about this. We'll just do the first three problems together. Okay, so number one, some cookie eaters are cookie monsters, so it is false that no cookie eaters are cookie monsters. Notice here that we're using our square of opposition and that it is, well, I'm using S and P, all S or P, no S or P, right? If you look down here, no S or P. I'm using those because I want to make sure that you remember that we're talking about subjects and predicates. So if we're looking, for example, at this first one, we're noticing that the subjects and the predicates are lined up, right? So we're talking about cookie eaters and cookie monsters. Cookie eaters is the subject, cookie monsters is the predicate. That's the first thing I want you to notice. These are legal immediate inferences. We're not, we're definitely being careful that we're not trying to use this on things that aren't actually immediate inferences. If our argument was something like some cookie eaters are cookie monsters, so it is false that no cookie eaters are pineapples, well, then that wouldn't work. We need the subject and the predicate to be the same in the premise and the conclusion. Okay, with that said, I'm not trying to trick you in any of these. They're just straightforward, but something to watch out for. Okay, so here's the way you use a square of opposition. Essentially, what you do is you take the premise and you find out what you know by computing it with using the square of opposition. So in this case, some cookie eaters are cookie monsters. If you notice, that just is a I type sentence down here. So what you really need to do is document that. So what we're working here with number one, in premise one, it's a true, there's my T for true, I statement. Okay, so what else do we know from beginning with a true I statement? Well, my favorite direction to go in is the contradictory, because it's just so easy. You know that the opposite one, the contradictory, is false. If one is true, the other one is false. So that's kind of my first move. Okay, what else do we know? Well, unfortunately, that might be it. If you notice, it's possible for A to be false because technically these can both be false, but it could also be true, right? Because E is false, so it's possible this one's true. What ends up happening here? Well, we actually don't know what's going on with A. It's actually undetermined. All this means is that if we begin with a true I statement, and that's all we have, because it's an immediate inference, 21 premise, really, there's no way we can know what's going on up here. So that's kind of a consequence of beginning with a true I statement. And by the way, because the A is undetermined, the O is actually also undetermined. Remember, these can, down here, the I and the O, they can both be true, or they can be true and a false. So we actually don't know what's going on with O. So in this particular case, we have two undetermineds, and we have a true and a false. And that's all we can know if we begin with a true I statement. So if we basically begin with the premise and see what else we know just from that information, this is all we know. We have a false E. So with that being done, once you've computed everything around the square of opposition, that's when you go back and look at your conclusion. You want to see what it says. And the conclusion seems to be suggesting that there's a false, so it's false. No cookie eaters are cookie monsters. That's an E statement. So according to this, that's a little messy. Let me make it a little cleaner here. But according to the conclusion, there is a false E statement. And according to me, that's neither. So false E. Well, that's what the argument says. What does the square of opposition say? Ah, look, there you go. You got your false, and you got your E statement. That means that this inference right here is valid. So if what the square of opposition says jives with or matches what the actual argument says, then you're good to go. That is a valid inference, and so this argument is valid. Okay, Let me clean up this whole mess right here, which is a lot of stuff. But let's now look at number 2. So number 2 says, it is false that some cookies are turnips. So no cookies are turnips. Well, let's begin by first documenting that we have here another I statement, but this time we're saying that it's false. So down here, we're going to go ahead and write false. It's a false I statement. Okay. So again, when we're doing immediate inferences, all we take is the premise information and go from there. We basically leave the conclusion alone. All we're working with is this one false I statement. Let's again begin with the contradictory because I love it so much. I know that if I is false, E is true, and there you go. I also know, by the way, if I have a false I know that that does something. It's called superalternation. If the I is false, that means that the A is false as well. So maybe one way to memorize this or remember this, I like to remember, that little saying, lies spread, right? So I just kind of reword it and I say lies rise. That means that if it's false down here, it's false up here as well. So that's what we know from a false I, that A is also false. And by the way, true, when it's up here, and either the A or the E, it does something similar. True goes down. Basically, I like to think, truth is down to earth, truth goes down. So if you have a true E, you also have a true O. Okay, so this is a nice complete square of opposition. We actually know a truth value for each of the types of sentences. So that's nice. No undetermineds in this one. Now that that's done, we return to the argument and we look at the conclusion. No cookies are turnips. So that is an E statement, right? And it doesn't say that it's false. So whenever it doesn't say it's false, you assume that it's true. So that means that we're looking at a true E statement. Okay, well, what does the square say? Oh, look at that. A true E statement. That means that this argument is once again valid. Okay, so now we've seen what an argument looks like when the square of opposition has some undetermineds in it. Now we've seen what it looks like when it's fully filled in. So let's look at the third one, and maybe we'll get an invalid one. I don't really remember, to be honest, but okay. So let's look at this last one. It is false that some cookies are not delicious, so it is false that no cookies are delicious. Okay, some cookies are not delicious. That is an O statement, right? So we begin by documenting that that's the premise we're working with, but notice also that it's false, which means that this is false. Okay, well, what else do we know from that? Well, let's not begin with the contradictory this time. Let's begin here with the superalternate. If O is false, we know that E is false as well because lies arise. By the way, you can basically at this point go in a variety of directions. You can use a contrary definition. You can use contradictories now. I mean, there's so many options when you're doing these that, you can kind of pick your own route. Let's go on a diagonal. Why not? So we did the E. Now let's go for the contradictory. If the E is false, the I is true. So let's document that. The A is also true, right? So there you go. Simple as that. Okay. It is false. Now we go back to the conclusion. It is false that no cookies are delicious. So no cookies are delicious is a no SRP statement. It's an E statement. And they're saying that it's false. And once again, we have one that does not match. Or sorry, it does match. So therefore it's valid. So this is three arguments here that are valid, where once you document or compute everything using the square, it turns out that the conclusion does logically follow. But if you ever get an example or a question where instead, let's just say that this argument had said, not that it is false, but it just said, so, let's just cross out that right there. So no cookies are delicious. That would still be an E statement, right? But then that would be a true one. And at that point, notice that those two wouldn't match. The E's match, of course, right? But that's a true and that's a false. So that wouldn't match at that point. So if you were to find something like that, that's when you know it's invalid. In any case, these three arguments are valid. It always matched. So yeah, that's how you do those problems.